Okay, so welcome everybody for the second day of AlCoVE. We have as first speaker Viviane Pons, and she's going to talk about the rise contact involution on Tamari intervals.
Hi, everybody. Thank you very much. I'd like to thank the organizers for inviting me to give this talk. And also, I want to thank you for organizing such a great online conference. So I'm going to talk about an involution on Tamari intervals. Let me start with some background and motivation. I'm going to tell you what is the problem that we are solving and why we are solving it, and also telling you that the intervals of the Tamari lattice are very cool objects. So the Tamari lattice itself is a lattice on Catalan objects. And so I'm going to define it a bit later. Right now, I'm just going to start with our story, which starts in 2005, when Chapoton found a really nice formula for counting the number of intervals in this Tamari lattice. So I put the formula here. You can see that it has some kind of Catalan flavor to it. It's also the formula that counts triangular maps. So I'm not going to talk about it during the talk, but it's a clue that these intervals are actually really nice combinatorial objects. So now, sometime later, Bergeron and Préville-Rattel were studying higher trivial diagonal polynomials, and they ended up defining a generalization of the Tamari lattice called the M Tamari lattices. So the Tamari lattice is a lattice on Catalan objects, and the M Tamari lattices are lattices on M Catalan objects. And they conjectured that the number of intervals was given by this new formula here, which is a generalization of the previous one, with now a parameter M. And a little bit later, it was proved that this formula is actually accurate by Bousquet, Melou, Fusier, and Préville-Rattel. And when they did so, they obtained a generating function for the intervals of the M Tamari lattices, and they saw in this generating function that they had a symmetry between two statistics, the number of contacts and the initial rises. But at this time, they could see it in the generating function, but they didn't have a combinatorial explanation for this fact. And actually, when Préville-Rattel wrote his thesis, he left it as a conjecture, and he left it as a kind of a bit of a more general conjecture than the original one in the paper, because he defined two series of statistics, the contacts and the rises. And he claimed that they were symmetric, but at this point he didn't have any proof, whether through the generating function or or any combinatorial proof. So that's why it was still a conjecture. So the goal of my work was to give a combinatorial involution that proves that the symmetry is there. So that's what we are going to do today. I'm going to present the case of the classical Tamari lattice, but it also works for the M Tamari, and you will have all the details are in the paper if you're interested, and I even have some extra explanation on this slide if people want to know more about the M Tamari case. But let's start with something easy. Let's start with a dig path. So dig paths are objects that are quite common. They are counted by the Catalan numbers. I think we are all quite familiar with them. So a dig path is just a path that starts at 0. It's made of up steps and down steps, and it never goes under the 0 line. I'm going to define some statistics. So the first statistic is the number of contacts. So you look at the dig path and you look at the number of time it goes back to the 0 line after the start. So on this dig path, the number of contacts is 2. And I'm going to define something a bit more general. I'm going to define the contact vector. So the contact vector, you start with this value 2. And then for each up step, you look at the path that starts right after this up step. You draw a line there and you look at the number of contacts of this new subpath. So in our case here, the value here is 2. And now you build a vector like this. So the next one is a peak. So when you have a peak, you have an empty path, so it gives you 0. Then here you have a 1, 0, 2, 0, 2, 0, 1, and 0. If you have questions at any point, do not hesitate to put them on the chat, and then I guess one of the organizers can interrupt and ask the question. So this is the first set of statistics that we are going to look at, the contacts. The second one are the rises. So the rises, the first one is the initial rises. You will look at the number of upstep at the beginning of your path. So here it's 2. And now I'm going to construct a rise vector. So it starts with this 2, and then for every down step, you look at the number of up steps following just right after. So here you have 2, 0, 0, 2, 2, 2, 0, 0, 0, and the last value is always a 0. This was always also the case for the contact vector, and so in the rest of the talk, I'm going to just ignore this last value because it's always 0. So why are we interested in those two vectors? First remark, if you have the rise vector, you can construct back the dig path. It's quite obvious because it's just a description of the path through the rises. It's also true with the contacts, even if it's not seen directly. If you know a bit about this object, it will seem obvious to you that you can construct back the dig path through the contact vector. So this is just another way to describe the path. And these two vectors have an interesting symmetric property. So if I look at the list of all dig paths, so now I'm looking at the dig paths of size 3, and I've written for all of them the contact vector in red and rises vector in blue. And there is a symmetry. So I'm doing a coupling of the dig paths. So the two dig paths up goes together, the two dig paths down goes together, and the one in the middle goes to itself. And if you look at the one on the left and the one on the right, we're actually switching the contacts and the rises. What we are doing, we're switching the contact vector and the rises vector, but the order is not preserved. So whereas here, for example, you have 2, 0, 1 as a on the down one, you have 2, 0, 1 as a contact vector, and it goes to 2, 1, 0 at the rises vector. So it's the same values, but not in the same order. And this symmetry is, so here's on an example on size 3, but you can check that it's actually true at all sizes. And now, so we find it at the level of dig paths, and the same symmetry, we're going to find it at the level of intervals. So this is what I'm going to explain to you right now. To do that, I need to define a little bit what is a Tamari lattice. So the Tamari lattice is a lattice that you can define on mostly on Catalan objects. So it has many different definitions depending on what your favorite Catalan object are. Here I'm going to show you on dig paths and binary trees. I'm going to give you the definition on dig paths. So the cover relation is called a rotation. It just consists, you take a step path like this and you move it up through this step there. So this one is going this path here. Now you can take this sub-step and you can move it up there. And now you can take this sub-step, sub-path and move it up there, and you obtain this one. And you could have also started there, take this one and move it up. You will obtain this path here. And now you take this sub-path there and you move it up like this, and you obtain this one here. Okay, and you have also a way to attach every dig path bijectively to a binary tree, and it was going to define you a lattice on the binary tree side, and this rotation operation can also be translated on the binary tree side. Okay, so how do we define interval there? Well, we're going to look at intervals as two dig paths. So I'm going to draw it like this for now. So one dig path is under the other. Be careful with this notation because it's quite obvious from the definition that if D1 is smaller than D2 in the Tamari lattice, then the path D1 is under D2. But be careful that it is not sufficient condition. For example, this pass here is under this pass there, but it is it true what I'm saying? Wait, no, this is not what I wanted to say, sorry. Up. It's this pass here, which is under this pass there, but it's not smaller in the Tamari lattice. It's not smaller in the Tamari lattice. So just be careful that being under is a necessary but not sufficient condition. But anyway, I'm looking at a Tamari interval here. So I have two paths, one small and one big, and I'm going to define what are the contact vector and rise vector of my interval. And the contact vector is given by the small path, the red path. So this is how I define it. And the rise vector is given by the blue path, the big one. This is just how I define those two things. And if I define it like this, then I will obtain the same symmetry on interval that I had on elements. So now I'm looking at the 13 intervals of the Tamari lattice on dig path of size 3, and I've written the coupling that you can do. And here you can check that if you look on the right, you will have, we have switched the rise vectors and contact vectors up to a certain order on the values. So basically here, for example, you have 2, 1, 0 is the rise vector, and it's going to 2, 0, 1. This is one example we had earlier with elements, and it's also, and it's going to be true on all the intervals here.
Okay, Viviane, there is a question on the chat. It says,
yes.
What is the alternating being above and below? What if the two paths alternate?
What if the two paths alternate? Oh, they never alternate because it's an interval of the Tamari lattice, so there is always one path that is below the other. It's a necessary condition, but it's not sufficient to be an interval, but it's necessary.
Okay.
So there is always a path that is under the other one. Okay?
Yep.
So now I'm going to show you, so now that I've stated the problem, I'm going to show you the solution, the involution. And we're going to start by the solution when we're looking only at dig paths, because this is a way that we will be able to understand the solution for intervals, even though this is not the way I found the solution, it's just the way I explain it. Anyway, so we'll start with a dig path here with the contact vector and rise vector. And I'm also drawing the binary tree, which corresponds bijectively to this dig path in the Tamari lattice. And the first, we're going to switch the contacts and the rises using very natural involutions on Catalan objects. So the first one is one that I call phi, and it's just reverse the dig path. So I'm just taking the dig path and reading it from right to left. So this is what happens to the dig path, and we can also understand what happens to the binary tree. It's an involution that I usually call the left border involution. It's rather classical involution on binary trees. It's just on every left branch, you switch, you're doing some kind of reverse of all the left branches recursively. So here, for example, this subtree there now is sent to this subtree there. Okay, and this one is sent to this one. So when you are used to binary trees, you know that it's quite a classical operation to do. And on the dig path, it's very easy. You just read it on the other way around. So what happens to our statistics? So for the contacts, you can see by applying phi, you will keep the same values, but you will just change the order in which you read them. So it's quite clear that what you obtain is just a permutation of the contact vector. And now for the rises, well, what we had as a rise vector here, because we're reading the path the other way around, is now another statistic, which is the right rises vector, reading the rises from the right, which is why I wrote it the other way around, so that you understand that we're reading the rises from the right.
There's a question if you are only reversing the left branches.
If you only reverse in the left branch, I don't understand the question, sorry.
Nicholas, if you can unmute yourself and ask.
I think the question said, are you only reversing left branches and not right?
Yes, I'm only reversing left branches and not right. The right branches reverse is another bijection that you can, it's another involution that you can do. Okay, so I'm doing the left one. Okay, so if things are clear, I'm going to move to the next slide. So once I have applied phi, so I've applied a permutation on my contact vector and I've changed my rise vector to something else. And now I'm going to apply another very classical involution, which I'm going to call psi. And this one is very easily readable on binary trees because it's just reversing left and right branches. So it's just a left-right symmetry on the tree. You can look, it's like putting a mirror over there, okay? On the Dick pass, it's not so easy to directly read, but it's also natural, and especially in the context of the Tamari lattice, because here I'm drawing you a small Tamari lattice of size 3 with the 5 element there. And what you have is that the Tamari lattice has this up-down symmetry. And this transformation is just the one that is following this symmetry. So it sends the down element to the up element and so on all the elements. So it's a very natural one to do when you're considering the Tamari order. And what it has this very cool property for us that it's actually switching contact vectors and right rises vector. So here you see that the blue line and the red line have been switched by the psi involution. So now, once I have this, I reapply phi. And what I do is that it's applying some kind of permutation on my contact vector, and it's changing my right rises vector into the usual rise vector. So in the end, what I have done is that I have applied phi, psi, phi. So I've just conjugated one involution through another involution. So it's still an involution. And I've exchanged the values of the contact vector and the values of the rises vector. So you can check here that in my original contact vector, I had 4 2s, 2 1s, and 4 0s. And now in my rise vector, I have 4 2s, 2 1s, and 4 0s. And same here, I had 5 2s and 5 0s. And now I have 5 2s and 5 0s in my contact vector. So this is a classical case involution. And this is what we're going to generalize to intervals. So to do that, I need to explain a little bit the different ways we have to see intervals of the Tamari lattice, because this is a key thing here is to see Tamari intervals with different objects to be able to generalize the involution the right way. So we have already seen the first way was 2 paths. So now we can transform each of these paths into a tree. So we obtain 2 trees. These 2 trees, we can use a certain labeling on them. It's just the research tree labeling. We label the node from left to right. 1, 2, 3, 4, 5, 6, 7, 8, and here's the same. So it's a standard labeling. There's no, I'm not making any specific choice here. There's only one way to label the tree this way. And this labeling is going to give me 2 new objects. One is the one there, which is called the Tamari interval poset. So it's a small, you can understand it as a poset. So you can see the blue and right edges as arrows that goes from left to right and down to up. And so you have 2 kinds of arrows. You have the blue ones and the red ones. The blue ones come from the tree on the right. And for example, here the rule is that, for example, you have 1, which is a left, it's in the left subtree of 2, so you have an arrow from 1 to 2. And here you see 1 to 2 here. And now the right arrows are given by this one. And the rule is the other way around. So if you have something that is on the right subtree, for example, 5 here is on the right subtree of 4. So it's going to give you a 5 to 4 arrow. And this is the one here. So, and you can construct the whole poset this way. It gives you an actual poset on numbers. And it's a really nice object because it captures the whole object of Tamari interval in one thing. It follows very easy rules. You can read more about it in the original paper. And it's going to give me a third interesting way to see intervals is this last object here. So let me clear that. It's a tree, and actually it's this tree here, okay? It's the same tree, except that now I've added little values inside the nodes. So let me explain to you what this means. When you have a Catalan object, it has a recursive structure, and this recursive structure is really mapped by the structure of a binary tree. A binary tree really reflects the recursive structure of a Catalan object. Where in the case of intervals, they also have this recursive structure, but they need some kind of extra parameter here, which is given, and this is what is on this node. So you cannot put any numbers, they have to follow a certain rule that I'm not going to express, but it's quite easy to see. And they give you a way to reconstruct the interval. So for example, so the rule to read it from this object is easy because, so here you have, for example, a 2 inside the node number 4. And this means that on the interval poset, the number 4 has 2 arrows coming to it, which are 5 and 6. And you can check here, you have a 1 inside the 2. Here you have indeed 1 arrow. And you have a 1 inside the 7. And here you have indeed 1 arrow. So this object, I call it a grafting tree, and it's very fundamental to finding this involution. So now I'm going to, yeah, there is a question?
Yes, can you recover the 2 original digs from the...
Yes. I'm not going to give you all the details, but yeah, you can recover the dig pass directly from there. There is a bijection from this one to this one. It's explained in the paper. And so from this one to this one, well, the shape of the tree is giving you the blue path. And I'm pretty sure you can recover the red path with the number there, but I haven't tried to make it explicit, the rule. I usually go through the tree or the interval poset.
Okay, and you have 3 minutes left.
Yeah, so in the 3 minutes that I have left, I want to show you how we generalize the previous involution to this. So our main problem is to generalize the first involution phi, because what does phi do? Phi reverse the dig pass. But the problem is that if I reverse both the blue and the red dig pass, I'm not going to get the Tamari intervals. This is what I told you earlier, that being under a pass is a necessary condition, but it's not sufficient. So what I'm going to do instead is I'm going to apply phi to the grafting tree. So here I've switched the red branch there. See, I had 3 trees there, and now I have 3. So like this big one here, now it's giving me this big one here. The middle one is still the middle one, and the little node there is there. Okay, so I switch those and I keep the values inside. And this, if I look at the rest of the interval, it gives me, so the blue pass has been reversed, but the red pass now depends on this little numbers that I've moved. And it's somehow the red pass is like following around the blue path. And the consequence on the statistics is still the same. So the contact vectors has been permuted, and the rise vector is now the inverse rise vector. So it's a rise vector reading the path from right to left. So now I need to apply, I need to generalize psi, but this is much easier because psi is actually compatible with the Tamari lattice. So what I'm doing, so you can see it very easily on the interval poset, because here I'm just switching all the blue and red. So for example, 1 is now becoming 8. So you see that here I had 2 and 3 going to 1. Well, now I have 6 and 7 going to 8. So all the blue edges become red edges, and all the red edges become blue edges. And on the grafting tree, it's not easy to see what's happening, but on the dig pass, I've just applied the Tamari, the up-down involution to the blue and the reds, and I've somehow switched the blue and the red pass. And I've actually switch the contact vector and rise vector. I'm sorry, there is a little problem with, I don't know if you see the down of this vector, but I've just switched the contact vector and the right rise vector. And now I can apply phi again. And in the end, what do I have? I still do the same conjugation as the classical case. So I apply phi, psi, phi, and this does exactly what I want. So it switches the values of the contact vector with the values of the rise vector. Let me clear that. Okay, so what do we have here? So we have a combinatorial bijection, which switches the contacts and the rises. It can be extended to the Tamari case. So this I have, if you're curious, I can explain a little bit about that. I have, it also has this nice property to preserve the distance in the Tamari interval. The distance is a maximal path, the length of the maximal path from the down element to the up element. So this is why especially intervals that are single elements, so same up and down paths are sent to intervals that are single element. And if you want more information, you can look at the paper, and you can also look at the SageMath demo, which is on my GitHub, and which allows you to play with the involution yourself, applying it to different intervals. And actually the involution is implemented in Sage now, if you look at Tamari intervals. Okay, I'm going to end up here. Thank you very much.
Thank you, Viviane. So for the questions, I'm going to start with a couple of questions on the chat. So Francois Bergeron is asking you, can this be generalized to chains? And I think it's considering the last part of like your last slide.
To chains, I don't know. I don't know because I don't have a good way to see chains. The way with interval posets doesn't work perfectly with chains. So I'd like to think about that. I'd like to better understand chains of the Tamari interval and see if we can do something, but I don't have a solution right now.
Okay. Then Maria is asking that it sounds like you have two equivalent Q analogs given by the totals of the contact and raise vectors. Do these Q analogs have any nice factorizations or other simple formulas?
So I don't know exactly about that, but this actually, maybe we want to discuss this with Francois, because I think he would be the one who would, because one of the motivation of that is that this Q analogs kind of appear in this work of François Bergeron and Préville-Rattel, and that's the whole motivation of the thing. So I'm not a specialist on that, but I know that this is the motivation behind.
Well, thanks.
Okay, and then Joel is asking, it looks to me that in the case n equals 3, that actually the multiset of contact vectors is equal to the multiset of right vectors without rearranging anything.
Mm-hmm.
That seems to be true in general.
So you mean in I don't think it's true in general. I don't know. I haven't looked at it. One thing is true, that you cannot switch them directly. That doesn't work. Do they follow the same combinatorial rule? I'm not exactly sure. Maybe, but I wouldn't bet on it like this. I would need to check.
Jane is asking that you mentioned that the interval count for the classical Tamari lattices coincides with a count of triangular maps. Are general maps or maps counted by some generalized interval count?
This is a whole set of study. People study this a lot, especially Wenji Feng, if you look at his papers. There are many open questions with that. Basically, we don't know very well. Like in the case of Tamari and generalized Tamari lattice, there's a paper from Wenji Feng that is actually explaining what kind of maps it counts. But we still have many open questions with that.
Okay, and the last question before we go to the break is, are you able to list the intervals where the two statistics are exactly switched, not up to order by Dorian?
I haven't tried, so I don't know.
Okay, so let's thanks Viviane again.
Perfect.